My name is Anthony Stefano. I am a research student and doctoral student in atmospheric science at UBC in the research team of Dr. Roland Stahl, and his team is the weather forecast research team. The project that I'm presenting at AHU this year in iPoster format is a discussion about how to make weather forecasts more accurate by using an observation source that is more reliable, ground-based, and is more widespread throughout southern Canada and the United States. And this observation source is called dual polarization radar. The concept of my research is basically to try and make forecasts more accurate by using these observations as a way to find weather forecast models that need some work or need some adjustment for higher accuracy. In particular, as they pertain to predicting extreme weather, such as precipitation, significant precipitation events, and flooding and mudslides. My work really looks into trying to, in order to compare the data sets of forecasts and observations, they need to be in the same level playing field because they are different kinds of data sets. So my research talks about using a simulator package software that converts weather forecast data into data that can be readily and directly compared with dual polarization radar data. And this overlay of data information can actually help us to find in new ways how forecasts can be made more accurate and what areas forecasts need some work. Currently, my main discovery is that it is possible to evaluate weather forecasts using this dual polarization radar data. Previously, it would have been much more difficult because there wasn't a direct way to compare forecast data with radar data. They're just simply two different data sets. But with the application of this brand new simulator package, which is called Polaris, P-O-L-A-R-R-I-S, what this allows us to do then is to convert the output from weather forecast models and turn those into what they would be if they were actual radar, if they were radar data instead. So then you can actually make that direct comparison and you can do error analysis and statistics. And this would allow us to use a higher quality, more commonly available data set for observations to actually talk about how forecasts are currently doing. It's sort of a new way, a brand new frontier in how we evaluate weather forecasts. I think my work is important because if we look at the context of the kind of weather that right here in British Columbia we've been experiencing, really extreme rainfall events in the last several months that have then led to flooding and mudslide occurrences throughout the south coast of British Columbia. It's something that really calls attention to the need for accuracy in weather forecasts. My research team is one where we really look closely at trying to make forecasts accurate in all kinds of different ways. My personal resolution, my personal method for doing that has been to go inside a weather model and look at the part that controls the creation of clouds and precipitation and see if those parts of the model can be made more accurate. They're all essentially equations like every model has, and those equations can be made more accurate if we have good observations to use to inform them. And those observations don't necessarily have to be ones that are limited in space and time. The great thing about using radar, any kind of radar, but in my particular instance, dual polarization radar, is that observations are sampled so frequently and the data is overlapping across most of the contiguous United States and Southern Canada, that if I wanted observations every 5 minutes, I could in theory evaluate a weather model every 5 minutes. And the only thing I would need to be able to compare the forecasts and observations is to get something that turns the weather data into equivalent radar data. And then they can be compared apples to apples. And that link is this new software called Polaris, which is a simulator. And it takes the weather output from forecast models and then turns it into something that can be compared for statistical purposes to these observations, which I think can be really instrumental in helping us to improve even short-term forecasts when we get closer to extreme weather events. I think one of the things that I find most exciting about this research is that I think it really does have the potential to have some real world impact. What I mean by that is, I think there's something to be said about using really good quality observations in a new way to look at weather forecasts under a different light. Usually, when we try to see how well a forecast does, at best we have things like station observations where at one station we can see how well something performs, or sometimes we have gridded observations that we get when we actually try to assimilate all the observations possible and use a grid to compare the grid of a forecast to the grid of an observation set. What we haven't yet done is used actual observation instruments that actually already create gridded fields with their observations and the way that they sample observations rather, and it's live and it's accessible very frequently at any given hour, and it's widespread and all the information overlaps with each other, so there seems to be sort of a continuous spread of information that we can access. We have yet to use that kind of information to evaluate weather forecasts. So I think it's really exciting just because it offers a new the potential for finding some new discoveries. Weather models and weather forecasts are so complex, and sometimes it can be really hard to look into them deeply to find areas that maybe are not as accurate or need a little bit more tailored work. And these kinds of observations would make that really, really interesting to discover and look into. So I think just the prospect of what this can offer is very exciting for me. My next step is to now conduct research with this new ability to evaluate forecast models. Right now, I'm running different forecast configurations. So looking at forecasts with slightly different, which apply slightly different ways of simulating precipitation and clouds. And then seeing for each of these versions of the same forecast that I'm looking at to see how each of these perform relative to these radar observations that I have. I'm using the area closest to British Columbia, which has enough data to study with. And this area would be the Pacific Northwest around the Olympic Mountains and the Olympic Peninsula in Washington State. And what I'm doing is trying to see now how each of these perform relative to each other and relative to these observations to find areas that may need some work. So for example, if I note that one forecast is producing too much rainfall or too much snow at different altitudes based on the radar data, and that seems to be a consistent problem among most of the forecasts that I've run, that suggests a bigger problem that needs addressing. And the basis of my thesis and my research is again to make forecasts more accurate as it pertains to predicting significant precipitation events, which then can then lead to flooding and mudslides and become hazards to civilians. And this is just my way of doing it.